Hello, welcome to the tutorial on how to do the bidirectional converter using MATLAB Simulink. Okay, so before we proceed, just want to show you a theory. Okay, so if you recall, what is buck converter? Maybe I should start with boost converter. Boost converter. Okay, so boost converter looks something like this: plus, minus, and then you have a inductor here, a MOSFET. Okay, something like this. Okay, you have this one and it goes here, and of course the MOSFET has diode. Okay, or maybe to avoid confusion, maybe just leave it there. Okay, and then you have a diode here. Okay, and you have a capacitor. Okay, and you have the load. Okay, so this is standard L, this one is S1, this is D1, this is C boost, okay, C boost, okay, and this is R out boost. Okay, this is V in boost. Okay, how about buck converter? So for buck converter, I draw it flip. Okay, so we start at the right hand side and then move on to the left hand side. So you get plus minus here, V in for buck, and then you have a switch there. Okay, maybe I should move this, or I just redraw this again. So plus minus V in buck, and then you have a diode here. Oh, sorry, not diode, the switch. I call this as 2. Okay, this one drain, source goes inside, this one drain, this is source. Okay, and then you have a diode here, and you have an inductor, and then you have a resistor. Okay, this is L, and don't forget the capacitor, C buck. Okay, and then this is the resistor, R buck. Okay, so it's something like this. And if you can see here, okay, you can relate this component actually. So this one is equals to this one. And for diode, remember when you buy a MOSFET here, actually when you buy a MOSFET, automatically it will include a something like a bypass diode. Okay, so automatically you can combine this one and this one together. Okay, you can see that. Okay, can you see it? Okay, and then for this one, you can see here, you can see it can be combined together. So this one is, I call it diode 2, D2, and this one is D1. Okay, you can see the resemblance. Okay, the difference is that, okay, maybe I use this one. You can see here C in and C out, and V in and V out. Okay, but for bidirectional, we usually use both voltage source or battery as a component, as the input and the output. So if we can transfer this into a bidirectional converter, this is bidirectional converter. Okay, we replace resistance with just a voltage source. Okay, no need for resistance. You can use resistance, but when you do a bidirectional, you cannot supply the power. If you use voltage source, you can either supply the power or generate the power. So that's why I suggest you use a voltage source. So we just take this one. Okay, take this one, take this one. We just use this one. So I get I use this as V in boost. Okay, V in boost. Okay, and then you have to put the C buck. Okay, you need to put the C buck. Okay, and then you have to put the inductor L, and then at this side you have to put the switch and the diode. So this one, make sure the direction is correct. Okay, and goes into here. Okay, so we call it S1, and then at this location we put the diode. Okay, this is the standard packaging when you buy a diode. When you buy a MOSFET, it comes with the parallel diode. So this is S1. Okay, so another one is S2. This one is drain, this one is source. Okay, same here, you have a diode here. Okay, represent this one and this one. Okay, and okay, something like this. This is S2, drain and source, and of course you need to have a C boost, and lastly a plus minus V in buck. Okay, so this is the bidirectional converter. So basically what happened is that if you want to operate as boost converter, so you just PWM this and off this. Okay, so basically it will become boost converter. Okay, but if you want to operate in the buck converter mode, so in buck converter, so you have to PWM this and off this. Okay, so when you off the MOSFET, it will just become diode. That's it. That is how the bidirectional converter operates. So I will show you how to implement this, because there is some hurdle when you want to implement the bidirectional converter. Okay, so we continue with the Simulink. So for this one, I use power library. So Simulink, Simscape, electrical, okay, specialized, okay, fundamental block. So I use power library. So of course you need to have a power guide. Okay, and then you need to have the source. So this one is V in boost, and then another one is V in up. Okay. Okay, next you need to have a element, series element. Okay, so you need a L here, so maybe 1. Okay, you have L, you have C bulb, maybe 30 is enough. Okay, technically there is no official way to design this, okay, but you can just use try and error method. So this one is C boost, and this one okay. Now we move on to the diode. Okay, power electronics goes to, sorry, no diode, you just use MOSFET here. Okay, you can see here in the MOSFET it's already have diode, so you can set the diode. For me, just remove the measuring port. The diode setting is here. Okay, just apply and then rotate. Okay, make sure the drain and source is correct. So you can see here the drain and source, and drain and source. Make sure you use the correct location. So this one is S1 and this one is S2. Okay, so S1 drain source, S2 drain source. Okay, so next goes here, and then don't forget the inductor here. So inductor has no polarity, so no need to worry. This one is just for measurement. Okay, for capacitor, yeah, it has polarity, but also no need to worry for this. Okay, because positive always follow the boost converter. Okay, so here, this one and this one. So basically this is the bidirectional converter. Okay, and then how to switch it. So to switch it, you have to go to the power electronic pulse PWM. So be careful, PWM, if you can see here, the operation, you only need one PWM at a time. Okay, so one PWM only. But the problem is that it is switching, so you have two type of switching. So I suggest you can either use coding or you can just use signal routing. Okay, how to use signal routing? You can use a multi-switch board. Okay, so multi-switch board here, you have only two data. Okay, so adjust it here. And here. So you look back at the design here. Okay, and then you need to have the constant. Okay, the constant is at the same one. Okay, this one. So basically you want to operate as buck or boost converter mode, you just write it here. So one is buck, two is boost, something like that. Okay, Okay, another one is for the duty cycle. Okay, this one is D. Okay, we have D. Okay, now we have to connect the PWM to here. So you can see here in buck mode. Okay, in buck mode you switch at switch 2 and switch 1 is 0. So buck mode is 1, so connect to 1. And for boost mode, the switch is as switch 1. So switch 1 will receive, but at boost, because this is boost, so you connect it at number 2. Okay, something like that. So this is how we switch the PWM for the bidirectional converter. So you have 2 switch. Okay, so this is for the control of the direction. Okay, and another one is the duty cycle, maybe 0.4. So we have complete this. So next what we have to do is you put a sensor here. Okay, you go to the sensor. Okay, measurement. Okay, the current. Okay, we don't need to take a look at the voltage because it is voltage source all the same. But for the current, you need to know the direction. Okay, so for current, I suggest you put here this one and this one. And another one here, inward. Here, make sure positive and negative is correct. Okay, and maybe you put some source here, some scope. You need to have 2 port. Okay, so this one and this one. So this one is II boost, and another one is II input buck, II buck. Okay, so make sure you the direction the direction goes out, this one goes out. Okay, why the direction is important? We want to look at the charge and discharging. Okay, direction. Okay, if I run this, it doesn't work. Why? Because the voltage is the same first. Okay, let us check. Okay, so the voltage here needs to be lower, maybe 50. Okay, actually there should be a calculation here, but I just use try and error. And another thing that you need to consider is that voltage supply and power converter cannot operate in parallel. Okay, because why? Okay, let me show you some mathematics. Okay, okay, let me show you some mathematics. So C equals I is equals to C dV over dt. Okay, dt. So you have a capacitor here, C, and this is the I. Okay, IC and VC. This one is plus minus VC. Okay, if you connect this into a voltage source, a stable voltage source, dV over dt C is equals to 0. So IC equals to C multiplied with 0 is just equals to 0. So basically the capacitor doesn't exist. But the problem is you need this capacitor, okay, you need this capacitor to filter out. Okay, you can see here you have inductor, and this one, if you put it outside here, you need to filter the diode. Okay, diode current, okay, diode voltage, because the voltage is not constant, and the capacitor will make the constant, the current, the voltage constant. So okay, sorry about that. I have something to do first. Okay, so we continue. So before we continue, don't forget to change the frequency. For this case, I put 30 kilohertz. Okay, so you can choose either, as long as it's above 20 kilohertz is okay. Okay, just don't choose it too small or too large. Okay, and less than 100 kilohertz. Okay, you have problem with the simulation because it is too heavy, or less than 20k because of the hearing range. So that one is, if you do hardware, it will be affected. Okay, so we continue. So let me show you what happen if you combine the capacitor here. Okay, remember that I said capacitor cannot be connected to this. Okay, you see here, you cannot run it. Okay, so the first solution is either you disconnected it, because it doesn't function. As I mentioned before, it doesn't function. But the problem is when you do this, see, there is no filtration. Okay, there is no filtration at the I bar. So I bar is this one. So this capacitor is used for filtration. Okay, so maybe I should check the recording first. Okay, for this case it's okay, but if the inductor is quite small, maybe 0.5, this effect might be severe. Okay, so still not severe. Okay, you can see here the ripple is quite large because of the switching effect here of the S2. And how about if you are operating at the boost mode? Okay, so if you run this, okay, so basically it cannot work, okay, because of the ripple. Okay, maybe I should increase to 0.7. Okay, so still the simulation doesn't work properly. Okay, due to the large ripple. So how we can solve this? So you can, the capacitor, you just add resistance. Okay, this is standard. Okay, usually in capacitor you have a resistance here. Okay, you just add it, resistance. Okay, so if you simulate this, okay, still not okay. Okay, it's still not okay. Okay, sometimes it's become okay, but sometimes it's not. Okay, so just leave it like that. Okay, maybe you want to see only one for the bulk mode. Okay, so I still not okay. So the next step is, okay, before I forget, okay, in real application, make sure you put RL. Okay, RL has internal inductor. Inductor has an internal resistance. So I suggest you put resistance. Okay. So this one is still not working. Okay. So to solve this, I suggest you add a L. Okay, you add a filter, a small filter, RL, around 50 I think is enough, 50 power of 6. Okay, so this filter is basically allows, okay, let me draw the board. Okay, so you have a source here, for example, a source, and the source is V something, V ripple. So basically you have a ripple, a DC component and AC ripple. Okay, so you have this one, you have a capacitor, and you have an inductor, and you have a voltage source, plus minus. So for example, this one is V ripple is equals to VDC plus VAC. Okay, so at this point this is a VDC. Okay, and at this point is VAC. Okay, this will VDC. Okay, and sorry, this one is V ripple. Okay, so if you do the Kirchhoff law, is allow the current to flow. Okay, the current to flow, you can filter the current. For example, here the current is something like this. If it is switching, something like this, something like this. Okay, this current can go here to IC. So that's why we have to put this one. Okay, to allow the voltage changes. Okay, so let me add this and rotate this. So 50, this one is not designed properly, so when you do this, better to design it properly. Okay, so this capacitor is around 100. Okay, this one is overly designed actually, so maybe this is 5. Okay, so let us run this. Okay, you can see now it is smooth. Okay, smooth operation. Okay, maybe I should show you. Stop. Okay, so run this and I change it to, so you can see here this is the current here, it's charging and then discharging. Okay, the positive become negative, negative become positive. Okay, and you can change the duty cycle 0.4 for example. Okay, something like that. Okay, maybe I will make a much more better this. Okay, okay, I have added the dashboard. Okay, if you don't know how to use it, you can look at here. You can add the dashboard function. So right now you can choose it. Okay, bulk mode or boost mode. Okay, you can see here this is the arrow, or it's bulk mode. It means that from here it goes to the left. Okay, in boost mode the current will goes from left to right. Okay, so this is the duty cycle. So let us try. Okay, so you can see there is bulk mode. Okay, increase the current. Okay, this is increasing the current. Okay, and then we can choose the boost mode. Okay, you can see here the current change direction. Okay, you can reduce the current. Okay, up to certain point it cannot work anymore. Okay, so maybe 3. Okay, you can do some analysis here. Okay, you can reduce it. Okay, at certain time it turn off, so this one cannot operate no more. But in boost mode it can operate, but in the negative side. Okay, other side. Okay, that is how you create this one, bidirectional converter. So I already changed this to the toggle, much more easy. So this is buck, and then I've changed this, it will go to boost mode. Okay, you can see the current change direction. Okay, so for boost I think it needs to be higher. Okay, if it's too low it will become 0. So this one is actually depending on this. Right now I don't design it properly, so maybe the result is become this way, something like this. Okay, maybe I should change it to higher value, 50. This is 100, or maybe this one is 75. Okay, so it should operate much more better. Okay, so I changed to bulk. Okay, it cannot operate no more. Okay, so basically you have to balance this up. Okay, 50, this is 100. Maybe this one can work properly. Okay, so in bulk mode you can operate until 0.5 only. Okay, so maximum is 0.9. Okay, and if you go to the boost mode it will goes to other way around. Also it only can operate until 0.4. Okay, after that you cannot operate it anymore. So that is the limitation. Okay, depending on the voltage, okay, you will limit it to that particular data only. Okay, so that's it. That is how you design, actually not design, fully design, how to implement bidirectional converter into the MATLAB Simulink. Okay, see you again. Okay, before we end the session, so this is the relationship when you are in the bulk mode and the boost mode. Okay, so for minimum, okay, so if you recall back here, okay, actually there are minimum and maximum. Okay, let me close this. Okay, not minimum and maximum, minimum. So you can see here the relationship between boost and bulk is 1 minus. Okay, so if you sacrifice, you choose the input voltage and output voltage much larger. Okay, so you can see here, so this is 100, so and then this is 50. Okay, so means that D min is 50. Okay, 0.5. Okay, and boost also 0.5. 1 minus V boost minus V1. So what it means that you can see here. Okay, Okay, so if you run as the boost here, okay, you cannot go more than less than 0.5. Less than 0.5 is will shut down. Okay, let me I run it again. So you can see here the current is much larger if you increase this. Okay, but if you goes to 0.5, it will become 0 for both current. Okay, that's why you have to calculate the minimum. Okay, same as boost. Okay, 1 minus 0.5 is also 0.5. So if you look here, if you increase it, it is much larger, but if you goes near to 0.5, it will turn off. Okay, so that is the limitation of this bidirectional converter. So for example, if you set it to 20, okay, if 20 means that the minimum for bulk is 0.2, but for boost is 0.8. Okay, let me show you. Okay, you can see here in the bulk mode, you can go up to, okay, it will reduce the current, but until 0.2 it will become 0. Okay, and you increase it, it will increase. Okay, so that is 0.4, but 0.2. But if you change to boost converter, okay, you can see here 1 minus 0.2 is 0.8 based on this formula minimum. So it needs to be more than 0.8 to operate. Okay, still no. Okay, after 0.8, yeah, you can produce the power. Okay, so for this type of converter, I suggest you to choose half so it can balance out. Okay, so 50 I think is okay. Okay, half of this. Okay. And for the relationship, this is the relationship, the input and the output. Okay, so for this one I think is almost the same, this one. Okay, but for boost mode you have to minus this one. Okay, so that's it, the relationship. Okay, to get the current, actually you have to find a paper that derive the relationship. So this one I derive it myself. So if you want to find it, you have to find a paper. Okay, I will upload this in Math World Exchange. Okay, so you can download the simulation. Okay, see you again. Thank you.